All right, so let's get started. Hello, everyone. Welcome to our second Youth AI talk of this year. I just want to give a warm welcome to some of our new audience members who are joining us from Australia. And thank you for joining today's Youth AI community. And we're very excited to have you here. Before introducing today's talk, I'd just like to give a quick overview of our last talk and then just give you a sneak preview of our upcoming talks. In our last talk on January 10th, the grandfather of VR and legendary inventor, Professor Tom Furness, gave a fantastic talk on VR. His talk is full of inspiration and wisdom. You're welcome to watch the replay of this wonderful talk at our YouTube channel at Youth AI Lab on YouTube. On March 27th, Dr. Kwabena Boahen will talk about brain-like computer chips in AI. Dr. Boahen is a professor of bioengineering at Stanford University with a joint appointment in electrical engineering. Dr. Boahen is one of the world's leading experts on low-power computer chips that work like the human brain. He's the founder of Stanford's Brains in Silicon Lab. Professor Boahen's scholarship is widely recognized and has won numerous distinguished awards. He's a fellow of the American Institute for Medical and Biological Engineering and of the Institute of Electrical and Electronic Engineers. Professor Boahen's talk is now open for registration, and you're welcome to register and join this exciting talk. On April 24th, we will host Dr. Alan Halavy. Dr. Halavy will focus on integrity in the age of AI, covering issues such as misinformation and fake news. Dr. Halavy is a world-renowned computer scientist, a world-renowned leading expert in AI, machine learning, and natural language processing. Dr. Halavy has been leading AI and big data research efforts in various companies such as Facebook, Megagon Labs, and Google. Dr. Halavy's talk schedule and topic are tentative. Registration will open later when Dr. Halavy's schedule is finalized. Next, my co-host Alex will share some logistics of today's talk.
Hi, I'm Alex. So before quickly introducing Professor Fang, I'd like to briefly go over the logistics of the talk.
I don't think we can hear you.
Oh, sorry. Sorry, Jeffrey.
Sorry about the technical difficulties, everyone.
So yeah, before.
Well, I can go ahead and handle the Q&A logistics then. I'd first like to just go over the logistics of this talk. So because we have audience members watching from both our YouTube live stream as well as our Zoom, we'll be doing Q&A through a platform called Slido. So either go to the URL I've just dropped in the chat here, or go to Slido and enter event code 57653. Feel free to submit questions throughout the talk, but we'll only be answering questions in the Q&A session at the end of Professor Fang's talk. Now, let me introduce today's speaker, Dr. Fei Fang. Dr. Fang is an assistant professor in the School of Computer Science at Carnegie Mellon University. Her research lies in the field of artificial intelligence and multi-agent systems, focusing on integrating machine learning with game theory. Her work has been motivated by and applied to security, sustainability, and mobility domains, contributing to the theme of AI for social good. Professor Fang has won a number of important awards at top AI conferences and was named in Future AI, AI's 10 to Watch by IEEE Intelligent Systems. Today, Professor Fang will share her work on integrating learning with computational game theory for addressing societal challenges such as infrastructure security, wildlife conservation, and food security. Let's give a warm welcome now to Professor Fang.
Thanks, Jeffrey, for the very nice introduction, and thanks, Alex, for taking care of all the logistics. So let me share my screen. So as Jeffrey mentioned, I'm currently at CMU as an assistant professor, and my research is on machine learning and game theory for social good. And in fact, in today's world, we're faced with many different societal challenges. We want to, for example, we care about environmental sustainability. We rely on rangers to fight against poaching in the front line to stop the population drop of key species like tigers, whose current population is just 1/20th of that 100 years ago. But the ranger resources is very limited, and it is important to really kind of understand how to best use these limited ranger resources. And we also care about security, we rely on security agencies to protect ourselves and critical infrastructure from potential attacks. But there's, again, always a lack of security resources. And beyond these, we also care about the population who are still experiencing hunger. And currently, there has been a lot of organizations like food banks, food rescue platforms trying to help these communities. And then in these cases, again, the operational efficiency of these platforms can still be improved. And actually, many of the staffs there are tasked with a huge cognitive burden dealing with many tasks. And what we want to do here in our group is that we want to leverage the power of AI to help tackle these challenges and also other challenges. And in particular, we're interested in using techniques in machine learning and computational game theory, and not only just apply existing ones, but also developing new ones to help address these challenges. Why we specifically use these two? Before going there, let me first introduce what is game theory and machine learning. It's just one slide introduction. So game theory, we all play games from rock, paper, scissors to kind of poker games to all kinds of board games like Wolf. And probably now you also play Among Us, this kind of games with multiple agents involved. And the study of game theory indeed stemmed from an investigation of the card games. However, now it is not just analyzing the entertaining games. Instead, it is the study of mathematical models of conflict and cooperation between intelligent decision makers. And now game theory has been used in economics and political science. Nobel Prize winners like John von Neumann, John Nash, and Heinrich Freier von Stackelberg are all game theoreticians. And to give you an all very kind of cute and concrete example to see like how game theory play a role in many different scenarios, here's a short video taken from a reality show, I believe. So let's see.
Balls in front of you, and they are the most important balls in the game. You will have one ball with the word split written on it, and you will have one ball with the word steal written on it, and you have to choose one or the other. You'll know which one you're choosing. If you both choose the split ball, you will split the money tonight, and you will go home with £23,625 each. If one of you decides to steal and the other decides to split, whoever has chosen the steal ball will go home with £47,250. But if you both decide to steal, you go home with nothing. Not one penny. You have a very difficult decision to make. Now, Chloe, you can have a happy ending to your story. And you can be on your honeymoon in Barbados, or you can be back in Doncaster.
All right, yeah, as we can see here in this very simple game, the outcome for these two players, actually for these two ladies, not only depends on the action that they choose, but also depend on the action chosen by the other lady. So this is a very vivid example of kind of game theoretic thinking. Now, if I'm one of the ladies, I need to reason about, oh, what action should I do? What action should the other lady take? And which action is kind of most beneficial to me? And in some cases, I may kind of try to understand, I would like to read the other player's mind if I can, and make the right decision, meaning the decision that can help me to win the most of the money. And this is kind of exactly what game theory can be applied to for the analysis. And in the problem that we discussed before, ranging from the security problems to the environmental sustainability problems, to the food bank and food rescue related problems, we all face multiple strategic decision makers who are interacting with each other. For example, in the security setting, the defenders needs to fight against the attackers. And in the environmental sustainability setting, the rangers need to fight against the poachers. And in the platform and food rescue platforms and food banks, there are multiple stakeholders involved in the whole process, and each of them may have their own interests or preferences or even goals, and the platform may also have their goals. So how to coordinate, how to understand the interest of all these stakeholders and to help the decision makers in this interaction to make the right decision is really crucial. And that's exactly why we want to use game theory to analyze these problems. And what is machine learning then? Machine learning is, in short, kind of trying to converting data to intelligence. As Professor Tom Michel at CMU puts it, a computer program is set to learn from experience E with respect to some class of tasks T, and performance measure P if its performance at tasks in T as measured by P improves with experience E. This is a very long sentence, but let's try to look at some concrete examples. So let's look at a task for predicting house price. And now you're given a lot of data describes in this region what are the recent sales of houses, and what is the number of square feet and the selling price of the houses sold recently in this area. And the dots, each dot representing the price and the number of square feet for one of the houses. And then here comes a new house shown on the x-axis, this little blue one. And you know how many square feet it has, and you need to predict what is the house price given the data you have at hand. So here, this task is clearly the predicting the house price, and the experience consists of all these data that you have at hand. If you can make a better prediction as you have this more experience, more and more the data about the recent sales, then you're set to learn from it. And same thing for a computer program. And what is this potential performance measure? In this case, a performance measure can be as simple as the difference between your prediction and the actual selling price of that house in the end. And as you may see here, we are in this task, we're using the number of square feet of the houses to make the prediction. And we often call this square foot here as feature being used. And the price instead is called the label for each of the houses. And when here comes a new house, we need to first extract the features of this new house, meaning how many square feet it has, and then predict the label, which is what is the price for this house. As another simple example, the task here is to predict whether the image is a cat, is to determine or classify whether the image is a cat or dog. And the experience you have is, again, a collection of images of dogs and cats. And the performance measure could be whether you have predicted or classified the image correctly. If you have many images, then it is like how likely or what is the probability that you can classify the images correctly. Okay. So this is basically a one-slide introduction of machine learning. And the reason why we want to use machine learning to help dealing with these societal challenges we mentioned is because in some of these domains, we indeed have a lot of data available. For example, in anti-poaching domain, there are many wildlife conservation agencies running on the ground and conducting patrols. And during the patrols, they would collect the data about their findings. It's like, oh, where did I find the poaching tools? Where did I encounter poachers and things like that? And this kind of data can help us to determine how to plan the patrols to fight against the poaching activities. So Next, for the rest of the talk, we will basically go through 3 example domains and how we use machine learning and computational game theory to help address them. The first is protecting ferries. Here, this is a Staten Island ferry. I don't know how many of you have been to Manhattan and taken this ferry before. It provides a crucial link between Manhattan and Staten Island, and it carries over 60,000 passengers a day on weekdays. So these ferries may present as attractive targets for an attacker who may ram a suicide boat packed with explosives into the ferry, as has already happened with attacks on the French supertanker Limburg and the USS Cole. So the question is how to protect the ferries. If you're a Marvel fan, you may recall that it is a Spider-Man and Iron Man who tried their best to protect the exact Staten Island ferry from sinking in the Spider-Man movie. But in reality, the heroes are actually from the US Coast Guard, who run these patrol boats, which are equipped with machine guns and can stop the attackers within a certain distance. However, there are multiple ferries running at the same time, and the Coast Guard only have limited patrol boats. What they used to do is that they choose one of the ferries and then ask the patrol boats to follow along with that ferry all the way, leaving the other ferries unprotected. And our game-theoretic solution, we apply game theory to this problem, and our game-theoretic solution is actually successfully deployed in the field since April 2013, and it has completely changed their maneuver in conducting patrols. And as you may see from this video, this is actually a video now is taken from the ferry. As we can see here, the patrol boat now is making a U-turn. This kind of simple U-turn pattern would never happen in their previous patrols. And you can also expect that in their previous patrols, because of the lack of variety, it becomes easier for the attacker to plan an attack. So if we look at this problem, what we can see is that there are many possible patrol routes that the patrol boat can take along the ferry line. For example, the yellow line here, or this orange line here, or this blue line here. And if the Coast Guard take any route deterministically every day, then this can be easily exploited by the attacker, because the Coast Guard is conducting patrols every day, but the attacker is not going to attack every day. Instead, a smart enough attacker would try to conduct surveillance to understand better like the pattern of patrols for the Staten Island ferry, and then kind of determine what time and what is the attack that they want to launch if they are going to plan an attack. So we model this problem as a so-called stackable game. This game has 2 players. One is a leader, who is the defender, and the other is called the follower, who is the attacker. And the reason why they are called leader and follower is because in this problem, as we said, the defender needs to conduct patrols every day. And if they are taking some kind of patrol strategy, that strategy will be observed by the attacker before the attacker decides what to do. So in some sense, the defender would announce their strategy that he's going to use in this game, and the attacker would observe that strategy and then respond. And that's why we call them the leader and the follower. And in this game, to describe what's going on in this game, we can try to write down the game matrix like this. So here we're calling the defender we're using each row to represent a possible action for the defender. In this case, it's like all the patrol routes that the defender can take. And we're using a column to represent an action the attacker can take. In this case, the attacker decides which target, which ferry to attack, and also what time to attack. Now, within this table, what we want to write down is the payoff values for the players. That means, for example, if the defender chooses the purple route and the attacker decides to attack target 1 at 10 a.m., what would happen? Who would be happy? How much loss would be incurred? Using some numerical numbers. And here we assume that these kind of numbers is already given in this format. That is, if the attacker attacks target I at time t and succeeded, meaning the defender was not able to protect the target at that point, then the attacker would get a utility of UIT. This is like, and if the attacker attacks but he fails in the attack, then the attacker would get 0. And further, we assume this is a zero-sum game, meaning whatever the attacker gains is what the defender loses. So because of this, we can basically fill in this table based on the UIT information that we have at hand. Here, the first number, the green number, it means the payoff for the defender. The second number means the payoff for the attacker. And as we said before, the patrol boat can only protect ferries when they are close enough to the ferry. There is a certain effective distance. And therefore, not all the patrol routes can protect all the targets at any time, right? And we also mentioned that if the defender used any deterministic patrol route, this can be easily exploited by the attacker. And therefore, it is very important for the defender to randomize in their patrols. So an example randomized strategy for the defender is like this. The defender say, okay, I'm going to take the purple route with probability 0.3, and orange route with probability 0.4, and blue route with probability 0.2. And every morning, I'm going to kind of use a random number generator to decide which route I'm going to take according to these probabilities. And therefore, the attacker, even if the attacker can conduct surveillance and try to figure out what the defender strategy is, the defender at their best can only figure out this probability distribution over these patrol routes, but the attacker would not know on a particular day which route will be taken because the defender cannot even tell for sure beforehand. And now the problem that we want to solve is what is the right probability distributions over these patrol routes so that the defender can minimize the attacker's maximum possible expected utility or expected payoff. So let's say that the defender is using this random strategy as shown, and the attacker decides to attack at target at 10 a.m. on target 1, then the expected utility for the attacker can be computed as basically the probability, the target utility at time 10 a.m. Times the probability that the attacker can succeed when launching this attack. And how to compute this? We know from the what we listed here that the target utility is simply UIT. And how to compute this probability of success? It is simply 1 minus the probability of failure. And when would the attacker fail? That's when the defender's patrol route can indeed protect the ferry at that time of attack. So therefore, this probability of success can be computed as 1 minus the sum of the probabilities for the routes that can protect the target I at time t. And the attacker is not dumb. The attacker, if he's smart, would try to attack the target at the time that can lead to the highest expected utility. And that's exactly why the defender wants to choose a randomized strategy that can minimize the attacker's maximum expected utility. So now we have all these elements ready, and we know that the task we're facing can be converted into solving the following optimization problem. It seems messy, but we have all the components at hand already. So here we're saying that the defender needs to choose the probability of taking each of the patrol routes, and the attacker needs to choose what time and which target to attack. And the quantity that they both care about is the attacker's expected utility. The difference is that the attacker wants to maximize, as we use the max here, maximize this quantity, while the defender wants to minimize this quantity. And of course, we need to follow the constraint that the total probability of protecting all these patrol routes should sum up to 1, and the probabilities have to be non-negative. And once we formulate the problem in this way, there exists the optimization problem solvers to solve this problem. And as a result, we can get these probabilities for taking each of the patrol routes. And in fact, from our on randomly chosen utility function, we can show that the potential risk measured by the maximum attacker's expected utility is cut down by half when using our algorithm. And as our work is brought to the real world, it has resulted in a radical shift in the patrolling tactics of the US Coast Guard. And the feedback from them to us is quite surprisingly good. And the Coast Guard called this shift in the patrolling as from point defense to zone defense, analogous to the basketball game, because now our patrol strategy would try to protect the target more frequently when the target's utility is higher, meaning when the target is more important. And you may wonder, when is the target more important? Well, I'll give you a few examples. In the morning rush hours, the ferry that moves from Staten Island to Manhattan would have many more passengers on it, right? So for these kind of ferries, they would have a higher importance. And also, when the ferry is closer to a terminal, then a successful attack would not only impact the passengers on the ferry, but also the passengers waiting at the terminals. So this is like how the importance of the ferries might change. And our game theoretic solution can take those factors into account when designing these patrol strategies. And also, they think our solution has improved the randomness of the patrols. And professional mariners also mentioned that there's an apparent increase in the Coast Guard patrols using new patrol schedules, while in fact, the number of patrol boats and the number of patrolling hours is actually the same as before. So this is an example to show how game theory can help to protect public, to ensure public safety and security. And fortunately, in this domain, a simple game model is enough. And however, for many other domains, the problem would become much more complicated. For example, in this wildlife conservation case, there are a lot of data available, but at the same time, the human behavior would play a very important role. So let's go further into this problem. In Uganda, lives of wildlife in this Murchison Falls National Park are threatened by traps and snares placed by the poachers. And we want to know what the poachers are doing. If we follow the standard classical game theoretic assumptions, it would say, oh, a rational player should choose an action that maximizes their expected utility. However, it doesn't really apply to this poaching scenario. What we observe is more likely like this. The snares placed by the poachers are distributed in different regions in the park. It's not really like go into the same location that can maximize the expected utility of the poachers. Then here comes the question, how can we predict where the poachers would place snares? Can we understand how the poachers make their decisions? And what we do is that we first try to learn this behavior model of the poachers by running a few human subject experiments. We designed this little game where there's a little poacher on the lower left corner. And then we ask human recruited to play this game in the role of this poacher, and he can move in this grid and determine where to place snares. And on the right-hand side, we show them what is the reward if they succeed in the snaring activity, and what is the penalty if they get caught by the rangers, and what is the probability that they can succeed, meaning how likely they will not get caught by the rangers. And we ask them to play this game multiple times in a row. And we collected the data from all these experiments and trying to understand what's going on. In addition to posting this game online and ask people from the Amazon Mechanic Turk platform to play the game, we also collaborated with multiple conservation agencies and ask the rangers and site managers on site to play this game, both on their computer and on their board. And with this data, we try to learn a model that can describe the poacher's behavior. The hypothesis we make is that the probability the poacher will place snare in location I or location J is higher if the so-called subjective expected utility is higher. And what is the subjective expected utility? It is actually a linear combination of a bunch of factors that might impact the poacher's decision making. Here we list a number of them. So we show that we assume that the subjective expected utility is this W1, a weight parameter, times the probability that they can succeed, plus W2, another weight parameter, times the reward if they succeed, plus W3, another parameter, times the penalty if they get caught, and W4 times whether they succeeded in the last round of the game, and so on and so forth. There might be many other features like these to be included. And here, the W's are the weights, kind of quantifying how important each feature is. And we want to learn these weights from data. We want to figure out the best value of W's that best matches what we observe from these human subject experiments. And with this learned weights, we want to predict the behavior of other human poachers. This actually led to some promising results in this online experiments and the experiments with the poachers. However, when we try to use these learned model to predict the poaching activity in the real world, we find that it is not really very effective, because the data we have in the real world is actually very different from the data that we collected from these human subject experiments. So we started collaborating with conservation agencies who have the real world poaching data. Here in this case, we collaborated with Wildlife Conservation Society and the Uganda Wildlife Authority, and they provided us 12 years of poaching data from the Queen Elizabeth National Park in Uganda. And they asked us to provide them the poaching threat heat map in this park. So how can we deal with this problem? So we take a slightly different approach. So first of all, we discretize this whole park into a 1 kilometer by 1 kilometer grid. And then we treat each grid cell as a separate target. And then for each of these targets, we're going to extract features similar as what we did before. So we're going to, the features we extract consist of 2 parts. The patrol effort related features, like what is the current patrol frequency in this area, and also geospatial features like, what is the animal density in this area, or what is the distance to the nearest road? Because in the real world, the poachers, when they place snares, say they want to poach elephants, then in the end, they need to bring the rhino horns or the elephant ivories to go back to the road so that they can sell them in the end. So these kind of geospatial features actually play a very important role. And for these features, some of them we are able to get them from our partners, from the conservation agencies. But for some of the other features, we have to extract them from the satellite imagery of that area. So now with the extracted features, what we want to do is that we want to predict for each of the locations whether or not there will be poaching activities in the future, ideally. So here we used the historical data, that is for a certain year for that location, we want to determine whether there has been poaching in that year in that location. And however, there's some tricky part here. If there has been some poaching activity found in that location in that year, then we clearly can say, okay, we're going to assign the positive label to this data point, indicating that there is poaching activity. However, if there's no poaching activity found in that location in that year, it is actually unclear to us whether there is poaching activity or not, because when the elephants or the wildlife are poached, they are silent victims. There's no one who would report to the police about the sighting unless the rangers go there and check what's going on. So if the ranger didn't go to that location, or if the ranger went there but was not able to find the poaching site in that location, then we don't have that data in our data set. So it is kind of tricky. And therefore, we have tried different machine learning methods, ranging from decision trees, neural networks, Gaussian process, to Markov random fields and others. And also trying to use a number of techniques to deal with this kind of label uncertainty. And in the end, we were able to learn a model that can predict for each location, what is the poaching threat? What is the level of poaching threat in that location? And based on these prediction results, we, in collaboration with these wildlife conservation agencies, we launched a number of field tests. The first field test is in the Queen Elizabeth National Park, where we selected 2 9 square kilometer regions that are not frequently patrolled before, but are predicted to be poaching hotspots by our prediction machine learning algorithm. We sent rangers to these locations, and they found all kinds of poaching signs. And unfortunately, they also found a poached elephant. So that means if they could have used our prediction tool a bit earlier, maybe they could have saved that poor poached elephant. But on the other hand, it also indicates that our machine learning model is directing the rangers to the right locations. And they are indeed poaching hotspots. And if we compare the snare hit rate, meaning the number of times they find snares in a month, we find that using our prediction model, their patrols, the snare hit rate during this test outperformed 91% of the historical months, and it is much higher than the historical hit rate. And inspired by this promising result from the field test, we launched a second field test that goes over 8 months. We chose 27 regions, each of them is 9 square kilometers. And then our machine learning algorithm, according to the prediction result of our machine learning algorithm, we divide these 27 areas into 2 experiment groups, the high threat group and the low threat group. And without telling the rangers which group the areas are in, we ask the rangers to go to patrol in these areas. And they patrolled for more than 450 kilometers. And when they come back and analyze the data, we realize that the catch per unit effort, meaning the number of snares being found per kilometer of walking in the high threat group, is 10 times higher than that in the low threat group. And also, as a base of comparison, the historical catch per unit effort is only 0.3. So as you can see here, the catch per unit effort in the high threat areas is much higher than the historical value. And this also indicates that the machine learning model can differentiate the high poaching threat areas from the low threat areas. And we also collaborated with other conservation sites. In the past few years, we worked with WWF China office and launched a field test in Jilin Huangnihe National Nature Reserve. In 2017, during a 2-day field test, we found 22 snares. And fortunately, during that field test, I went on patrols together with our collaborators there. And as you can see, I'm removing the snare from the tree. And I have to admit that I didn't really see that snare myself. It's the experienced rangers pointed to me that, Fei, there is a snare locked on this tree. And then I looked at that tree for a while and then finally figured out, oh, there's a snare. So it's really not easy to find the snares placed by the poachers. And In the last year, in 2019, we also launched a 1-week field test during which they found 42 snares. So these numbers are much higher than what they usually find in those areas. So it sounds very promising. We have the machine learning model. We can predict which areas have higher poaching threat, but that's not really the end. Because remember, what we want to do is we want to predict, or we want to determine where to go patrols so as to reduce the poaching activities. And therefore, we want to plan the patrols building upon the machine learning model. Like during our field test, we didn't really plan patrols very carefully. Instead, we directly say, okay, let's pick some 9 square kilometer regions and ask the rangers to go to those regions. However, in reality, they need to take a complete patrol route, meaning it is a pass. And if we design the pass correctly, we can really improve the overall patrol efficiency. So what can we do here? We treat the machine learning model that we have learned as a black box, and then trying to reconsider it or view the model from a different perspective as something that takes as input the current patrol effort and outputs the probability of snaring or detecting snares at location I in the current time period. And now our goal is to solve the optimization problem where I want to determine the value of xi so as to minimize the total, the sum of yi's. And we need to also take into account the scheduling constraint because remember, we said that the patrol route has to be a pass. And in fact, in most of the cases, the patrol regions have the so-called patrol posts, and the rangers need to start from the patrol post and come back to the patrol post at the end of the patrol. So once we have, and these scheduling constraints can also be described using linear constraints. And overall, it becomes a mathematical programming problem, an optimization problem that can be solved by existing solvers. So this is how we generate these patrols. And so far, so good. We have found the patrol routes. However, that's still not the end of the story. The reason is in some of the target site for deployment, the terrain can be very complex. For example, this is a site in Malaysia where we were interested in. And as you can see, it is a very hilly region. The elevation change is just not eligible. And if you don't consider these terrain information, then you may plan the patrols on this grid that we have created, and this could be a patrol route that you get. And it looks fine on this 2D map, but if you check the 3D map, you would see that it is ridiculous. The rangers just cannot follow it because it has to go over the mountain, and it cannot, and because this route asks them to just go through the mountain in a straight line, which is impossible. So we had to understand how terrain makes a difference for patrols. And to do so, we went to Malaysia and conducted a trial patrol together with our collaborators from Panthera and Rimba, 2 NGOs that we're collaborating with, to see how patrol really works. And this photo is taken before our 8-hour working in the jungle. This is me and my PhD advisor, because this is the work that I did during my PhD. My advisor, Milan Tampe, who's now already at Harvard, and also our co-author, Professor Bo An from Nanyang Technology University. So we're all very excited at this beginning and looking forward to the patrol. And then this photo is taken towards the end of the patrol. We are all exhausted, and our collaborators told us, oh, there are still 500 more meters to go. So from this experience, we realized that patrolling is really not easy. And also, during the patrols, we figured out that we need to take into consideration the detailed topographical information. And in addition, the ridge lines and streams are usually easier to walk along. So that's also the reason why I step in the water, because it's just flat. So it's very easy comparing to walking up hills and down hills. So now, with this first-hand experience, we come back to the lab, and there's a major shift in the design of the algorithm. So we switch from a grid-based thinking to a route-based thinking. Now we focus on terrain features such as ridge lines, like this on the right-hand side, and streams because we know that the elevation change along these route segments is much more gentle. And also, as a result, these route segments would have higher animal traffic, and therefore the poachers would also focus on these route segments when they place snares, and so should the patroller when they patrol. So we use this hierarchical modeling approach, which treats these terrain features as route segments and build a virtual street map of the area. And this is what the street map, the virtual street map, look like. So kind of trying to connect the ridge lines and streams. And now we can plan patrols on these virtual street map. And the resulting patrol routes are compatible with the terrain, and it's easier for the rangers to follow. And based on this work, the algorithm was able to deploy in Malaysia, and these are photos taken during the patrols. And if we look at the patrol routes that are actually executed, here we show that the orange line indicates the recommended patrol routes, where the black line indicated the actual patrol route that they took in the end. So before, when we had this grid-based thinking, the rangers cannot follow the suggested route at all. It's very hard to do what we ask them to do. That's not their problem, that's the algorithm's problem, because we didn't plan the route that is suitable for them to take. And with this route-based thinking, now it's much, they were able to follow this route segment, they were able to follow this recommended route. And they also give us the feedback that it is much easier to follow with this. And also, if we look at the number of human activity signs found during these patrols, we can see that they found many more human activity signs as guided by these new patrols. And also during these new patrols, they are guided to some places that they've never been to before. And we call that part the explorative new patrol. And as we can see, again, these new areas that they've been to, due to the suggestion of the algorithm, also led to a lot of findings of human activity signs, again indicating that the algorithms are leading the patrollers to the right direction. And putting everything together, we summarize our work in this anti-poaching as this PAWS framework, the protection assistant for wildlife security. It learns the poacher's behavior from the existing data, and then also trying to model the terrain given the protected area's terrain information. And then based on these two parts, it tried to reason about what is the best strategy for the rangers to take and suggested patrol routes to them. As the rangers execute these patrol routes, they can collect more data and feed back to the system to make more, to improve the poacher's behavior model. And going beyond these on-ground patrols, in the recent years, we also investigated the UAV patrols, the drone patrols. In some of the conservation sites, especially at night, it's very hard for the rangers to patrol as they do it during the daytime. So they would have these drones equipped with thermal infrared cameras to fly in the conservation area, and the rangers can simply sit in the truck nearby and wait until the drone spotted any poacher. However, it is a tedious job for the ranger to sitting there and watch the video all night. So we developed this deep learning based application tool to automatically detect humans and wildlife from the videos taken by these UAVs in almost real time. And this video is taken from a test run in South Africa. And these humans in the video are not really poachers, they are actually rangers because it's a test run. We want to see if the algorithm is working properly. And in addition, building upon this application tool, we further discussed build game-theoretic models and discussed how to plan the patrols that coordinates the movement of the allocation of the UAVs, the drones, and the human patrollers. because as we know, both the UAVs and the rangers are limited resources we have, and there are not enough rangers, and therefore we suggested to use the flashlight to deter the poachers. And in fact, in practice, they already used this flashlight in some of the regions. And this is a video showing that the poachers running away as they get caught by the drones. So what we want to do is that we want to find the best allocation strategy for the rangers and the UAVs, so that they can coordinate with each other. What do I mean by coordinate? Well, if a UAV spots a poacher at some location, and if the ranger is too far away from the drone, then the ranger cannot get there and catch the poacher on site. So it is important to determine where to allocate them. And in case that the UAV is indeed in the location that is very far away from the ranger's current location, we need to use that flashlight in a strategic way to deter the poachers. It is kind of similar to what we do, what we sometimes see in outside houses. So, at some of the houses, they would put the sign that this house is protected by surveillance camera or something like that, so as to deter the burglars. But you may also imagine, well, maybe for some of the houses, they put the sign outside of the house, but there's no really the surveillance camera on in their house. And the similar idea can be applied here. When we use this flashlight to show to the poachers, we want to convey the message that the rangers are coming, you better run. But sometimes the ranger might be very far away and we're not able to really come here and catch the poachers. However, if we adjust the probability of using this flashlight properly, we can maximize the defender's benefit in this whole protection for the wildlife. So similar as before, we build game models and build mathematical programming-based algorithms to solve the problem. Okay, so that's the second part, was showing that how we use game theory and machine learning for wildlife conservation. And for the third part, I'm only going to make a relatively brief introduction of what we have been doing. So this part is about the food rescue. Indeed, food waste and food insecurity coexist around the world. The report says we waste up to 40% of our food globally, which means it is more than 1.3 billion tons annually. That's a lot. And at the same time, 1 in 8 people go hungry every day, and the situation can be worsened due to the pandemic. So how can we do to help? The food rescue platforms is trying to help through rescuing the good food. What's going on here? How this food rescue platforms operate is like this. So the food rescue platform would post a rescue request to a smartphone app that they have. This rescue request says, okay, restaurant A has some leftover food that are still good but unsaleable, and we're looking for volunteers to deliver this, to rescue this food and send them to a local community B who are in need of food. And once this rescue request is posted, the volunteers who are registered on this platform, on this smartphone app, can claim that rescue. And once they claimed it, they just go to the pickup location to pick it up, and then deliver the food to the recipient. And that would be the complete process. And these photos are taken during my own experience for working as a volunteer for the platform. So we work on this project in collaboration with a food rescue platform here in Pittsburgh. And we learned that a challenge they face in their operation is that they are uncertain about whether a rescue will be claimed and completed by the volunteers. Because this is not like the volunteers are not under any contract with the platform. So the platform always need to worry about whether each of the rescues can be claimed. So what do they do then? Well, they would send notifications to the volunteers, reminding them that there's a rescues in need of your help. However, if the volunteers get too many of these notifications, they will fall into the notification fatigue. Oops, sorry. And in addition, they would ask the human dispatchers to intervene. However, the human dispatchers need to take care of all the existing rescues that are on the platform, and if they do it because of the limited number of dispatchers they have on the platform, the dispatchers will be overstretched. So how can AI help in this case? We can learn a predictive model of the rescue claim status. We want to use machine learning to help determine which rescues need special attention from the human dispatchers, so that the human dispatcher don't need to keep their eye on every single rescue they have on the platform. Also, we can use this data-driven optimization of the intervention and the notification scheme, so that we can determine who to send the notification to, so that we can avoid the excessive notification to help retain the volunteers. And to see how we actually did it, for the first task, if we have a rescue come in, then we will first extract a number of features from this rescue, including the timing-related features, the weather-related features, the location-related features, like what is the time needed what is the distance to complete this, the travel distance for this rescue. And then based on those features, the machine learning model would predict whether it will be claimed by the volunteers. And the machine learning model we built here is kind of similar to the subjective utility model that we built as before. It has several weight parameters that needs to be learned from the data. And we used the so-called stacking model that combines decision trees with Gaussian processes and neural networks. And as we can see here, the stacking model did a really great job in like predicting the status of the rescues. And in particular, it has an extremely high precision. It's almost perfect. I put the star in the 1.00 thing, indicating that the actual value is not exactly 1.00. It's just after rounding and the multiple random splits, it can be it averaged to this value. But this almost perfect precision means that all the rescues that are claimed to be claimed, that are predicted to be claimed by our algorithm, are indeed claimed in reality. And this is crucial because that means we are not making a lot of false claims about the, we're not overly optimistic about the rescue claim status. In fact, if the precision is very low, then it means there are many rescues that are predicted to be claimed, but are in fact not claimed in reality. This will be particularly concerning because it can lead to the failure of a rescue, which is clearly undesirable. And in contrast, if we report a little bit, if we're a little bit too over pessimistic and bring to human dispatchers' attention more claims than necessary, it is still okay. It is less costly than the missed rescues. And here we show using the ROC curve, indicating again that this machine learning model is doing a good job comparing to some of the other models. So that's the prediction model part. And we also dealt with this optimizing scheme. We want to optimize the intervention and notification scheme used by the smartphone app. So what they're doing right now is that when the rescue is published, they would send out the first wave notification for all the volunteers that are within 5 miles of the pickup location of that rescue. And then they will wait for 15 minutes. If the rescue is still not claimed, they will notify all the volunteers on the platform. And in addition, if it is getting close to the deadline of the pickup time, the pickup deadline, and it is still not claimed, then the human dispatcher would jump in and trying to call some volunteers that they are familiar with and ask them whether they can help for this particular rescue. And according to our data analysis, we noticed that more than 900 volunteers would get the first wave notification on average. However, only 44.6% of the rescues are claimed by the volunteers receiving the first wave notification. That means a lot of the notifications we send in the first round are kind of not very effective. And our goal here is to try to improve this whole scheme. The first attempt we had is to try to change the values of this X and Y and Z here. Like we want to determine to what range of volunteers we should send the first wave notification to, and how long should I wait before sending the second wave of notification, and when should the human dispatcher jump in? Yeah, so we again formulating this as an optimization problem and then trying to find out the best values of X, Y, Z. And with our optimization, let me skip these mathematical details, just mention that with our approach, we were able to recommend a alternative intervention scheme to the food rescue platform, which has been deployed since January 2020. So that's it for today's talk, and I hope that by through these example projects, you have an idea of how AI can potentially help address these societal challenges. And I'm happy to take questions at this point. Yeah, thank you all for having me here.
All right, so thank you, everyone. Yeah, thank you, Professor Fang, for the wonderful talk. I think my audio previously wasn't working, so I'll hand it over to Alex to ask the first question from Slido. Again, if you joined late, just a reminder that we'll be doing Q&A through a platform called Slido, and I'll just send a link again in the chat if you don't have it.
Yeah, so here's one question, just that's from Anonymous, but the question is, how do you resolve the black box problem where the model's decisions aren't explained, which could lead to unethical decisions being made by the model?
Yeah, that's a very good question. So here, we also, many of the machine learning models we have tried are also interpretable ones like decision trees. And in fact, when we collaborate with the wildlife conservation agencies, for example, we started from really simple decision trees to make sure that they understand what the machine learning model is doing, and they can interpret that, they can understand it, and they can even give us feedback on whether they think this is a reasonable one or not. And as we test these machine learning predictions in the field, they notice that there is an apparent increase in the number of snares they found, or the number of times that they encounter poachers. And at that point, they realize that this machine learning models can indeed help them. And because of that, now we build the trust between them and like us, and they also kind of know that the machine learning model can of value. So with that, we can build a more complex model that can provide more accurate predictions measured by the data that we have.
Okay, so looking on Slido, I see there's another popular question, which asks, for the poaching problem, which type of ML model did you end up using at the end, and why that model is better? Since I believe you discussed several types of models, ranging from decision trees to deep neural networks.
Right, so in our latest iterations, we find that Gaussian process and neural network-based models work the best in terms of the prediction accuracy, as well as the and in the earlier versions, we also had this decision tree ensembles that works well too. So I think the reason why they work well is because in these domains, we tried our best to kind of augment the data set like we're not using the original data set and directly apply the off-the-shelf methods. Instead, noticing that we're facing this label uncertainty in our data set, we have to augment the data by upsampling the positive data points, downsampling the negative data points, and also elicit information from the human experts, like the rangers and the site managers, to further sample additional data points to make it a balanced training set, and then learn from there. And I think the reason why these models works is that first, we tried to use ensembles, which is really helpful in terms of increasing the robustness of predictions, avoiding overfitting. And second, these models that we use are expressive enough to represent the potential relationships. It is more powerful than the linear model that we have tried with the human subject experiments. And as a result, they were able to better capture the connections of the features we observe and the poacher's behavior.
Okay, so another question is also from someone anonymous, is how would you suggest students start learning machine learning and develop algorithms for problems that they're interested in?
Yeah, so I think nowadays, luckily, there has been a lot of easily accessible resources online. I believe that you can find courses on both YouTube and Coursera, for example. And in addition, there are books, ebooks that are freely available, including the deep learning book. So these are all great resources. And for beginners, I think probably taking some online courses as a starting point might be helpful. And once you get a rough idea and you want to have a hands-on experience, to learn from doing, I think that's also extremely helpful. I know that there are Kaggle challenges, for example, and many of those challenges require the use of machine learning models, and you can probably also learn from other solutions to deal with the problems, those well-defined problems in those kind of platforms.
Okay, the next question has to do with how ML can solve culture problems, and the question asks for references, for instance, like the Oracle Bones script, which is like a current problem that a lot of anthropologists can't decipher. So they were wondering how AI could potentially be used for culture applications like that.
Yeah, unfortunately, I'm not an expert in that, and I'm not familiar with the one that you just mentioned. I know that there has been a lot of more and more people kind of care about this part, and yeah, unfortunately, I won't be able to provide any reference on that.
Okay, another question is, how would one select which features to extract for the model?
That's a very good question. So first of all, we discussed with our collaborators and jointly come up with these factors that might impact the human's behavior. And second, we try to distill the features. Like initially, we may have like 30 or 40 features, but when we train the model, we will try to figure out like which features are really crucial. Can we try to not use these many features? Can we try to use a subset of them and still get a reasonable model? And we would try to like come up. So that's kind of the basic process. We come up with a large set of features based on the discussions with the collaborators, with the domain experts, and then trying to distill the features through learning.
All right. Another question was more on like the software specifics, asking about what frameworks did you use for your work, or was it existing libraries, or were there custom implementations?
Yeah, so you may see that for the mathematical programming part, we have a lot of like optimization problems to solve, and for those ones, we typically use Cplex and Gurobi, which are like very efficient mathematical programming solvers. And for the machine learning part, we use the various packages through the various projects we have. We had tried TensorFlow, PyTorch, and also, I think for some of the projects, we also tried scikit-learn. So these are all things that we have tried before. Any other questions?
All right, so I see one last question, which I think we'll wrap with. So someone was asking about what technology was used to detect poacher and animal activities on the monitor TV. Was it image processing or AI?
Yes. So we use the algorithm in computer vision, like faster RCNN and YOLO, to detect objects in the figures, in the videos. And we worked with Microsoft engineers to make the whole process more efficient through like parallelized computing, cloud computing, and things like that.
Okay, so I think that's it. That was the last question, I think. So thank you, Professor Fang, so much for taking your time and giving such an excellent talk today on how we can use machine learning to address societal problems and societal challenges. And that's a wrap. Yeah, thank you so much.
Thank you for inviting me. It's my great honor to be here, and thank you all for coming to the talk.
All right, so we're going to wrap now. Thank you, everyone, and